Okay, so I think the streaming is kind of working. So one thing, if you're directly watching this or you're logged in via Meet, you can increase the screen size by changing the tiling layout. So I hope you all know how to change the layout in Google Meet. If you change it to Spotlight, currently it will be in auto for most of us. If you change it to Spotlight, okay, that is what I have done, so that you'll be able to see more of the slide. Okay, so yeah, let's continue. So what have we done so far? So we have been looking at unsupervised learning. This is the last week of unsupervised learning, and we have done representation learning, which is PCA, and then we did the nonlinear version of it, which is kernel PCA, and then we did clustering, which is kind of quite different from what happened in PCA. And finally, we are coming to estimation. So if you remember the first week, as Professor Arun had mentioned this point, that comprehension is something that is achieved via compression, meaning the whole point of unsupervised learning is to understand something about the data set that we have with us, and that understanding, which is what we mean by comprehension, is achieved via compression. Okay, so that is the overall theme with which we started, and let's quickly go over how that theme is applicable to these 4 weeks. Okay, so if you have n data points in RD, then in the case of PCA, can someone tell me how this compression is achieved? What are we compressing, and how is that helping us? Anyone?
By creating vectors means we are reducing. Like if we have two dimension, then a line is made which will represent the whole data in some sense. Yes, there will be error, but somehow it will represent data.
Okay, okay, right. So that is kind of what we do. We, instead of calling it a line, for line is correct, but in the case of general d-dimensional space, you have k directions, right? Instead of one line, we have k lines, and typically k is less than d, right? So you're compressing. Instead of having all d directions to explain your data, you're choosing k directions, not necessarily in that in the standard basis, but in a different kind of a basis. You're choosing these k directions, and you're achieving this compression. How do we compress in the case of clustering?
We make clusters representing instead of giving whole data, we make clusters, or
Right,
we make clusters.
right. So we make clusters, and the cluster mean is kind of representative of all the points in the cluster, right? So instead of having all the endpoints, we are only going to look at k points. These k points are nothing but the k means of these clusters, right? So that is how we achieve compression in clustering. In estimation, as we will see, and most of you would have seen through the lectures, we achieve this compression via k parameters of some probability distribution. Okay, so this theme of comprehension via compression is something that you'll have to keep in mind for all the 4 weeks that you've studied, right? So that's kind of a unifying theme for unsupervised learning. So estimation, the basic idea of estimation is that you are trying to model the way data is generated, right? So data is generated in some way, and I'm trying to model that. So some of the questions that we ask in estimation is, okay, where does this data come from? Okay, so what is the process that generates this data? Okay, so how did it arise in the first place? And moment you ask that question and you say data is generated through some process, once you fix that process, the next question that you ask is, what are the parameters that are going to control this process? Okay, so let's say data is ones and zeros, then you come up with a process which is flipping a coin, and the coin has a parameter p, right? So you are interested in that parameter p because the moment you know what the parameter is, you can in some sense throw away the data, right? Because you have the power of now generating the whole data using this parameter, using this modeling process. Okay, so some of you might be wondering how is it different from clustering and representation learning that we have seen so far. One way to understand it is in the case of, so we move from the present to future in the case of clustering and representation learning, which means that you start with some data set and that is it, right? That is all you are given and you have to somehow make sense of it by explaining the pattern. So the patterns could be best k directions or the patterns could be clusters, right? But you accept that whatever data is given to you is what you have and you see what can be done with it. Okay, so this is the first two methods that we have studied. The difference from these two methods as far as estimation is concerned is that you kind of go to the past, right? So the moment you have a data set, you don't immediately start doing something on it. Instead, you ask the question, what gave me this data set, or who gave me, by who I mean, what process gave me this data set? Okay, so you're kind of moving back in time and you're asking this question, okay, what generated this data set? Okay, so this fundamental difference you have to keep in mind with respect to estimation and how it is different from the other two techniques. Okay, so
Sir, in
yeah.
the if we see the last case, if we want to give our data to someone else, first two can if by the first one and two, that means by PCA and by clustering, the another person can understand the data not exactly, but he can come close. But in the third case, he may not come even close also.
That is true. So if you're, I think what you're meaning is if our story about the data is wrong, then the whole point of estimation is gone, right? Is that what you're saying?
Yes, that also, and instead, yes, that's correct. That which model we take, but instead that because it is probabilistic, that year 10101 are given, then he may not understand this was the data initially, which I was giving to him. He may not understand this was the data because he will lead to many such like instead of this pattern he may get 11101.
So that is where our assumption comes in, right? So we assume that the exact sequence is not really important because we make this assumption in our modeling process that the points are drawn IID, right? So that is a risk. I agree, but that's like kind of if your sequence is important, if the sequence information is important, then the models that we have studied in this week are all in the wrong kind of models to fit the data, right? So yeah, I get your point. So this that again comes down to choosing the model and also on the kind of assumptions that we make, right?
Right.
Okay, so moving forward, you have this Professor Arun keeps talking about this generative story, right? So you see a set of observations here, they're all ones and zeros, and the generative story that you try to come up with is that these points, these observations could have been the outcomes of coin flips, right? Heads or tails, heads is one, tails zero. So if you flip the coin here, let's say 6 times, then these are the observations. So this is our story, or this is our moving back in time and saying that this is how data points are generated. Okay, so and this is the Bernoulli distribution, as you all know. And we say that X is sampled from a Bernoulli distribution with parameter P. Okay, and our whole goal is to estimate this P using the data. Okay, and the moment you estimate P using the data, you have achieved the compression that you have been looking for. Because you can explain the whole data set using just a single parameter P and a distribution called the Bernoulli. Okay, so I hope you all understand how compression is being achieved and how we are understanding the data in this way.
So I had a question.
Yeah.
Does the value of P never change in the EM model?
Value of P never changed. Sorry, can you
Like how futuristic is the model? Can it be in terms of coin flips? Yeah, I understand. If there is a bias in the coin, it might be 0.6, 0.7, whatever. But there are values which might change over time. For example, the mileage of a car, it might deteriorate over time. So, can we use a model like this for predicting what will be the general average of the value?
no, right? So this is again where the sequence starts mattering, or this is not a static. So this is a static distribution, right? So what you are suggesting is kind of a dynamic distribution which changes over time, right?
Yes, yes.
So that has a temporal component associated with it. So this is too simple for that, right? So we
Got
may
it.
have to look at other generative models. By the way, these are all some kind of generative models. We can also call them that way because we are trying to understand the generative process behind the data. Okay.
Okay.
So moving on, let's. So this is also something you
Sir,
saw. Yeah.
yes, sir. In the previous slide, I had one doubt.
Yeah.
Yes, sir. In this, the value of P is 4/6.
The value of P is not known. We can estimate it to be 4/6. I mean, it's a
Yeah,
good
yeah. Means
estimate.
we can estimate if by estimation it is 4/6.
The estimate for P is 4/6. Yeah. One
Yeah,
of the
sir.
estimates. Yeah.
That means if I go in the past and I try to cause the coin 6 times, and this set is repeated 600 times, and I get 400 times this data. May not be 400, but highest probability is that I will get this set.
Okay.
Sir, is I'm right?
Yes. So you are generating 6 data points 400 times, is it?
Yeah, I am. Yes, I am tossing 6 coins, and now this becomes one set, and this set is made now. This is made for 600. I try this for 600 times, and in that case, in after trying this, the highest probability that 400 times I get this data. Is this correct? I'm saying.
Okay, so I would look at it slightly differently. Instead of saying 600
Here
times,
I am not able to understand what is this P. What is this probability? That's
P is the bias of the coin that you are flipping.
yeah. Yeah,
So
but
which
how
means
generative this generative sense is not connected with this P. I am not able to understand this connection between generation and the value of P.
they are connected, right? So if P is 0.5, then if you flip a unbiased coin 1000 times, then roughly 500 times you will get heads, 500 times you will get tails. So it is connected to what you observe, right? So the value of P determines, in a probabilistic sense, what you are going to get as observations. If P is 0.9, then you will observe out of 1000 coin flips, 900 of them, roughly 900 of them will be ones and 100 will be zero, right? So that is what P is.
Okay, sir.
Okay, so yeah, so another instance is when your data set is having real numbers like this. So you can think of this as heights of people, right? So 165 centimeters in centimeters. So if you have some data like this, then the generative story that you will go for is uh, the distribution rather. Now from now on, we can talk about the distribution that will generate this data. What will it be?
Gaussian.
It will be a Gaussian, right? So a Gaussian distribution, and the parameters governing them will be the mean and the variance. And you say that these observations are sampled from this Gaussian with these parameters, right? So the whole of week 4, if you want to understand, what we are essentially doing is parameter estimation, right? Which we have already done in stats 2, but we are just giving it a machine learning flavor here. Okay, so for parameter estimation, you need the following things. You need data, and then you need a model which tells you the generative story. Okay, and this model is going to have what? Parameters, and the whole point is to estimate these parameters. Okay, so this is the sequence that you have to always remember. And the methods are mainly, we have discussed two methods in this week. One is maximum likelihood estimate, and the other is Bayesian modeling or Bayesian estimation. We will quickly go through them. But first, we look at MLE. So MLE depends on two things. What are they? Likelihood, maximum likelihood estimate depends on two things. What are these two things? Anyone
One
know?
is parameter.
Okay, parameter. Okay, what is the other one?
So the data.
Yeah, so the data and the parameters, right? So I've called it the model here, but so it is basically the parameters and the data. Okay, so as you correctly pointed out, it is the likelihood depends on the data and the theta. Theta here stands for the parameter of some generic model. It could be Bernoulli, Gaussian, whatever, right? So assumptions, these are important, very important, and you will see this everywhere in machine learning. Wherever you go, you will see most of the times IID assumptions, right? So this will be IID assumptions will be used in supervised learning from weeks 5 to 12, right? So you'll also see them now. The only case, some of the case, situations where it will break, as some of you pointed out, is in sequence data, right? Where you have some kind of sequences in place. So for example, if you're analyzing speech data, right? So speech data has a natural time component associated with it. So, or text data. If you look at text data, right? If I am uttering some word or if I'm writing down some sentence, then the current word is kind of dependent on all the words that came before it, right? So in such situations, the IID assumption will break down. So independence will break down basically. But we are not going to be worried about all that. I just told that so that you get an idea of that there are situations where IID doesn't hold also. But for our course, IID holds, and I hope you all understand what we mean by this. P of xi given xj is P of xi. And identically distributed means you take any two random variables, the probability of xi is the same as probability of xj. Any questions in IID assumptions? Okay. So MLE for Bernoulli. So what is the likelihood for this data? If the Bernoulli has parameter P, what is the likelihood of for this data?
3 by 5.
3 by
No,
5.
likelihood, right? Not the likelihood, maximum likelihood estimate. I'm asking for the likelihood function.
P to the power 3, 1 minus P square.
Okay, P cube into 1 minus P square. That is correct. What will be the log likelihood?
Product of
Okay, as an expression, can you tell me what it will be?
It will be 3 log P plus 2 log 1 minus P.
That is right. Okay, 3 log P plus 2 log 1 minus P. Now, if you are going to differentiate it with respect to P, this is what you get, right? So, I hope all of you did this exercise because this is important that you learn to do this. You end up with the maximum likelihood estimate to be 3 by 5. So, in general, it is 1 by n times sigma xi, so which is just the mean of the sample, right? So that is the ML maximum likelihood estimate for the Bernoulli distribution. So this is, I'm just here and there I'll be plugging in some activity questions. So you can just tell me the value and we can move on. What will be P hat ML? You just tell me the ratio, that's enough.
6 by 15.
That is correct. Okay, so we are moving on. 6 by 15 is correct. So now, what is the answer for this? So did you understand what possibility and probability are? They are two very close. They are two closely related terms.
Highly unlikely, like
Possible, it is possible that we can observe this data.
improbable.
How much
Is
there
correct.
are? 3, 3, 6. Yes, improbable because there are less that.
Right. That is
Uh, there is a possibility of seeing this data, but the probability of that seeing that data, this data is very less.
okay. Great. Okay. So that is it. So it is possible but highly improbable, as you have all pointed out. So this is important because at the end of the day, what we can do is model something, right? And because the whole thing is probabilistic in nature, we cannot say that because my probability is 0.8, out of 10 observations, exactly 8 of them should be hits, right? This is something that you can't posit. You can only say that in general, this is what will be observed, right? But you can't exactly go and say that, okay, there were 10 observations and 8 have to be hits, right? So I think you all understand that. Another question from the activity questions. Is this equation correct?
Yes,
Okay, why is this correct?
Independent.
because
Independent.
independent.
Independent of
Okay, so how is this different from saying that P of xi given xj equal to P of xi? How is it different from that, or is it the same?
like PFXN is independent of all. It's the same for all xi. Yes, it's the same.
Okay, right. So this is essentially the same as the previous one. And what all that we are saying is that it is independent of everything that came before it, right? The last observation is independent of all the other things that came before it. So I have one question, trick question here. If I know that x1 to xn minus 1, if I know the values, then don't I get more information about what xn will be?
No,
Yes.
Why?
we may say that if this is the probability, but we cannot definitely say that that's the value you can take.
Okay, right.
If the distribution is identical, then it should be same.
Right. Okay. So that is correct. Just because we have seen n minus 1 data points, we may be tempted to say that we have a lot of information, but ultimately the nth observation depends on a coin flip, right? And that coin flip has a probability of p, right, which is completely independent of what x1 to xn minus 1 were, right? So it is correct. Now, one more question. So tell me the question, tell me the answers for the first two, then we'll discuss the last one. First, so are xi and yj independent?
Xi and Yj are
Yes,
independent.
sir, they are
Yes.
independent.
Okay. Are they identically distributed?
No.
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 Okay. What happens when px equal to py?
Then they
It
will be identically distributed, sir.
Okay. Why they are identically distributed then?
Same probability.
Okay, that is correct.
No,
Okay,
sir,
so
they are from different sets, but
that is correct. But yeah, they are from different sets. But what do we mean when we say something is identically distributed?
as
The
maybe
probability distribution will be same for that.
Right. So the probability distribution is same, right? It's still Bernoulli of P. Assuming that Px equal to Py equal to some P, then P of Xi equal to P of Yj will be equal to that P, right? So they have the same distribution governing the two. So this is why the question had this Px not equal to Py. If they are the same, then it's essentially it's as good as tossing the same coin n times here and then tossing the same coin again another n times, but just calling them x1, x2, and y1, y2. Right? So I hope it's clear what we are saying here.
Excuse me, sir.
Yeah.
Sir, I have doubt in activity question in this regard only, identically distributed part. So it is in activity 4.1, question number 7.
Question number 7. Yeah, that is the next question.
Okay, okay, sir.
Okay, so so what we are doing here is,
Excuse me, sir. In the last question, I just have a doubt.
yeah.
So, by just only saying the these probability models are equal, we can conclude that they are identical.
Sorry, you're asking why, how we can say that?
No, no, not how. Like this is the only sufficient condition to say they are identical, or there are something else we need to take care.
To my knowledge, that is all, because we are saying that they're identically distributed, right? So what all we are saying is that the distribution governing these two random variables is the same, right? So distribution governing x1 or xn whatever is Bernoulli of px, and the distribution governing these random variables is Bernoulli of py. Moment px become py, then they are essentially coming from the same distribution, right? So they are identically distributed.
Okay, they are coming from the same distribution, but like in this question only, the system from which they are coming are different actually, because x and y.
So so you look at it this way. I have two coins, so there are two boxes having two coins. Box is x, another box is y, and the bias is px, py. So if px is not equal to py, I understand they are two different systems. But moment px is equal to py, you are essentially having the same coin in. I mean, you're having similar coins in both the boxes, right? So you press box 1, you get a value. You press box 2 or box y, you get a value. But the coin that is being used to toss is the same, right? Or similar, having the same bias. So it has to be identically distributed, right? In that sense.
Okay.
Yeah.
Thank you.
Yeah. So now we extend the story and have two coins in a box, okay, with different probabilities, or with same probabilities. It doesn't matter, but the probabilities are p and q. Okay, so how do you generate a data point? You pick one of these two coins and you toss it. Now the probability of picking the first coin is alpha, that is given to you. Okay, so there are two coins inside a box which you can't see. Someone inside the box is picking one of these two coins with the probability alpha, picking the first coin with probability alpha, second coin with probability you know what, and that person is tossing the coin, and only thing that the box outputs is the number 1 or 0. So now what can you say about the observations that come out of this setup?
Identical and independent.
Okay, so that is what we'll have to show now, right? So what is p of x equal to 1, right? So
Why it was identical?
we'll come to that. We have not yet proved that. We'll come to that while we see they are independently distributed. That much are you all convinced? Because
Yes, sir. Yes.
Yes,
okay.
sir.
Okay, so what is p of x equal to 1? What expression can you write?
Alpha p plus 1 minus alpha q.
Okay, so I'll just break it down. So there are two steps, right, in a coin toss. So in making an observation, what is the first step?
Picking a coin.
Picking a coin. So what is the probability of picking the first coin?
Alpha.
Alpha.
Okay, so if I say the coin is, I index the coin as 1 and 2, z equal to 1 is coin 1, z equal to 2 is coin 2, then I'm going to write the following expression. Do you all agree that this expression is correct?
Yes.
Okay, so this is the probability of picking coin 1. Once you have picked coin 1, this is the probability of observing 1 given that the coin you toss is 1. Okay, and so what makes us write this plus symbol here instead of something else?
Because we don't know which coin.
Or any.
Yeah, it is. Yeah, it is an OR. More importantly, what is it? These two events are exclusive, right? I can either pick coin 1 or I can pick coin 2. So this is a plus. Okay, so now we can go ahead and write substitute this with value. So P of z equal to 1 is alpha. What is P of x equal to 1 given z equal to 1?
It's P.
P. Okay, so P of z equal to 2 is what?
1 minus alpha.
1 minus alpha.
Okay, and this is
1 minus alpha.
so okay, sorry, this is not 1 minus p. I made a mistake here. It should be q. Okay, so yeah. So now do you understand why it is identically distributed?
No, sir, but P is not equals to Q, na? So why?
Okay. So the point is, what is this quantity? Call this quantity some theta. What I'm saying is that the probability of seeing a 1 is some theta. Okay, which is the same as saying I am flipping one coin with probability theta. Okay, so it's you can as well replace these two coins setup with a single coin with probability alpha p plus 1 minus alpha into q. Okay, so they are identically distributed, right? So whenever you draw a coin, so draw an observation, it's going to come from this distribution Bernoulli of alpha p plus 1 minus alpha into q.
So, sir, you combine these two things, like you are not dealing these two coins explicitly, but you are making it only one, and you are saying the probability of getting x equals to 1 is this in a combined form.
Yeah. So I'm just making this argument that you can replace this two coin setup with a single coin setup, which is Bernoulli of alpha p plus 1 minus alpha q, and that I know is identically distributed, right? All the data points coming from that distribution are going to be identically distributed
Because it is a single coin.
single coin. So even without this argument, you can kind of reason saying that as far as I'm concerned, this whole box setup is kind of isolated, right? And I'm going to pick coins from the same, or rather pick numbers from the same box. So they should be identically distributed, but that's kind of not very convincing. So we argue this way by saying that we can replace it with a single coin.
So, sir, if we are not taking this argument, we are replacing it with a single coin, and we know that there are two coins. Is there any other theory that we can prove it that both the things are identically distributed?
I'm not at present. I don't know. So yeah.
Good afternoon, sir.
So
Yeah.
if these coins have a bias of like P have different probability and Q have different probability, then they won't be identically distributed.
Why not? They will still be identically distributed, right? So P and Q, you can give P and Q basically any number, any value between 0 and 1. Alpha P plus 1 minus alpha Q will be some fraction, right? So it will be some value between 0 and 1.
Sir, suppose P is 0.7 and Q is 0.5. Then, sir, it will be not identically distributed.
Why not? Why not?
Because, sir, both the probabilities are different.
Because
but we don't know which coin is going to be picked. Any one coin can be picked, so you just agree two of them.
Yeah, see, it's the simplest.
Go continue, sir.
Yeah, see, the simplest way of understanding is that's why I said you forget about this two coin setup and see what we have shown is that I can replace two coins with a single coin. Do you agree to that statement?
Yes.
So the moment I do that, I can immediately see that they are all identically distributed, right? So see, P of x equal to 1. I'm not saying that this is P of some xi equal to 1 is dependent on that particular case, right? So I'm saying that for any general x, any random variable x, and that assuming a value 1 is kind of only dependent on P and Q and alpha, right? So it is dependent on that setup, right? And that is all. So any two observations have to be identically distributed.
So, sir,
Yes, sir. That means we have to forget that there were two coins. We have to come to this one point, and from there we have to think, yeah, this is the setup.
Yeah, yeah.
so I understood this part. But sir, if we have the two things, suppose two coins, and we are not combining it as a whole, and we know that the probability of both the coins are different. So I generally used to say that if the probability of both the things are different, then they are not identically distributed. So is this right, or we should use another thing to identify that whether they are identically distributed or not?
Sir, may I?
Yeah.
Yeah. So, Shrishti, you can what you are thinking, what I can understand is you are drawing the observation from tossing one coin and then drawing another observation tossing from second coin, and then you are comparing it. If you are comparing this way, then they are not identical. But here we are observing it after, you can say, you picking one coin out of two coins, and then checking what is it is a head or tail. In that sense they are identical. Suppose there is a man standing and you are just asking him, then what did you get after tossing a coin? It's an head or tail. So we are limited to that person only. We don't whether we know that there are two coins or more than two coins, it does not matter.
Okay, so we are just looking at one box, and we are not bothered about there are two coins and what is the probability. We are just looking at the combined part.
Yeah, because we have to take care of from where we are drawing the observation. We are treating they are not two separate observation.
Hmm. Because they're in a box.
Yeah.
Okay. Okay. But if we have to deal with two other things, then my approach was right, no?
Yeah, if you are drawing the two observation from two different, you can say, toss coin.
Okay. Suppose there were two boxes, then my approach was right.
I think yes. Sir, may you please correct me if I'm wrong?
If you are using two different boxes, that is the previous question.
Good afternoon.
But that will be
Just one point here. Sir, just one point here for clarification regarding this question. And once while explaining the difference between identical and independent, sir has used the same analogy, almost same analogy, that when one flips a coin, coin flip coin, even though they are independent of each other, they are not identical. And I want you to clarify on this and the current question, how similar or dissimilar the situations are here.
I asked these questions in the activity questions just to clarify that point in the lectures. If you have two different coins which belong to two separate sets of observations, which is what this question 4 is, then they are independent and identically distributed only if px equal to py. If they are not equal, if the coins are having different probabilities, then they are not identically distributed.
Okay, sir. Okay, sir. I got your point.
Right?
I just want to clarify that px equals to py is the only constraint we have to look for the identically distributed one.
In this case, yes, yeah. So if we pick up some kind of a more complicated scenario, then we may have to reason further. But here, since the distribution governing the whole process is Bernoulli with a single parameter p, it's enough if you look at the values of px and py.
Okay.
Okay, is this clear now,
So
or shall we?
in this question, in this question, how can we compare
Like
the
this
statement regarding question number 5? In this, we are having two coins in a single black box, correct? Now, in this situation, how can we compare with the example given by sir in the lecture regarding the difference between independent and identical events?
this is independent and identical, right? So what Sir gave in the lecture should be compared with this question, right? Now this is a different question. What we are saying here is something is happening inside a box and you are not privy to that. So we are saying that whatever happens in the box stays inside the box. You could toss 2 coins, you could toss 3, 4 coins, but finally what matters is what you observe, and therefore they are going to be independent and identically distributed, right? You are just going to be getting some values, and they're all
So
drawn from the
what
same.
I'm understanding is that what sir gave the example is like in that example we know for sure that there are two different coins coming from different say bunches of coins, and that is why they are not identical even
Yeah,
though independent. Here it is a black box kind of thing, and we are not sure whether there are 2 coins or 30 coins or whatever. What we are getting is only the output, and
exactly.
that is why we can, even though it is a 2 coin or 30 coin, that becomes immaterial. What is the output becomes the crux of the matter, and basis that we can replace n number of coins inside the black box as a single coin basis the probability calculated.
Exactly. Yeah. Yeah. That is what this last line is saying, right? You don't know which coin was chosen or what happens inside the box. You only know that the
Yeah, so
coins. Yeah,
basically, it basically boils down to saying that ultimately you are not bothered about the number of coins. You only need to understand what is the output is, and even if there are 3 coins or 4 coins, you can always replace that with a probability
single
with
coin.
you can replace that with like a single coin. Okay,
Exactly. Yeah.
thank you.
Okay. So I think we have to move on. Just a correction in case some of you have not noticed this. It should be Q, right, and not 1 minus P. We'll correct it later.
Sir,
Yeah.
can you move to the last slide, please? Yeah. So if like you have
And
taken this
but we cannot, if we correct it to 1 minus p to q, then this p of x equal to 1 and then p of x equal to 0, the summation should be 1, correct?
Which summation should be 1?
We are calculating p x equal to 1. Similarly, we will calculate p x equal to 0 and the summation would be 1,
Yeah, the
correct?
summation should be 1. Yeah.
Oh.
Okay. So ideally, we shouldn't be spending any more than 2 more minutes. Yeah, on this question.
So I'm just asking if the clause expression is not like, because we know like this is a Bernoulli distribution by the closed form you achieved. If this is not the expression we are getting, then we can't say that it is identical or not, right?
We assume that it is Bernoulli, right? So it's a modeling assumption.
We assumed and we got this closed expression, and we finally look at like this is resembling with what we known for Bernoulli, right? But if it instead of one like this expression alpha p plus 1 minus alpha q, there is some other expression we got. So we can't say right anything about whether they are identical or not, because we don't know ultimately what's the uh, distribution it belongs to.
No. Distribution is what you choose, right? Model is under your control. The data may not be under your control, but the model that you choose. I choose a Bernoulli because I observe ones and zeros.
Yeah.
The model is your choice.
So no, at what basis you have made this particular conclusion that it belongs to like it's identical, just because the close expression you get it, or something else here?
No, not closed expression. It is P of x equal to 1, right? So any x does not mean x1, x2, x3 or anything, right? It governs any x, any observation, right? So this is, if you observe a random, if you take a observation at random, that is going to have a Bernoulli distribution of alpha p plus 1 minus alpha q. That is, there is only one distribution. I don't have like n distributions for n observations, right? I have only one distribution, and therefore that distribution happens to be identical across any number of observations I happen to have.
So by this, like we can like there are some examples, which known examples I can say, where this is not identical. So how can we conclude?
Yeah, please tell me those known examples.
No, I don't know Like there might be some examples.
No. See, I don't understand why. What is the confusion in saying that this is identical? Why
No.
is it not identical?
I'm not saying. I'm not going against what you are saying. I'm just asking. What made you conclude that it's identical? That's what I'm saying.
What makes you not conclude that this is identical? Tell me your argument for showing that this is not identical. I mean, for me, it is obvious that it is identical.
I'm not going against what you are saying.
No. See, you can go against me also. I don't mind. We are having a discussion. You tell me. You please explain your argument for saying that you are not convinced that this is identical. What is your argument?
You are taking you just taking it in a wrong direction. Just I'm asking what are the sufficient conditions, because
see, I am not offended at all. I don't understand your question. I don't understand what angle you are coming from.
I'm just asking the second expression, because this alpha p 1 minus alpha q, like you got this ultimately you got this expression, and I know like this belongs to Bernoulli distribution. I'm saying if by applying the first condition, first line statement, if you don't got this particular expression, will you say it is a identical distribution or not? That's what I'm asking.
I will still say it is identical, right? P of x equal to 1 doesn't depend on any index. It doesn't depend on any particular observation that I'm picking up. It only depends on some parameters alpha, p, and q.
Okay.
Okay, see, you must be clear. If you want to draw some examples, you must tell me those examples, and if you ask me, I will be able to help, right? More than this, I am not able to help at this stage.
Okay,
so we shouldn't have spent so much time on this, because this is like stats 2, right? We need to move on, right? So yeah, so why do we work with log likelihoods rather than just likelihoods?
So we were having the 8th question after the 7th in the activity, and I'm not able to see the question right here. So are we going to deal with it later on, or is it there in the slide?
What is the 8th question?
So there were two coin setup. One has probability 0.9, another has 0.3, and we have to replace this two coin setup with one coin setup, and the question is asking what will be the probability of that one coin setup.
That is what we did right here. Alpha p plus 1 minus alpha into q. You have to just substitute p equal to 0.6 and the other one as 0.3, and you will get the answer. Alpha will be half here.
Okay, sir. So, sir, in these kinds of question, can we add some of the probabilities and divide it by 2?
No. You can't do that, right? Because only if alpha equal to half, you can do that.
If there are two coin setup, then we can divide it by 2. If there are more than 2 coins, suppose 3 or 5, then we can divide it by 5 or 3. If we have to convert into one coin.
No. Only if so. See, in that question, we have given that the coins are chosen uniformly at random, which means alpha equal to half, or alpha equal to 1 by k if there are k coins. If that clause is absent from your question, then you can't divide it by the number of coins. You have to look at what is the probability distribution governing that picking of coins in the first place.
Okay, so sir, we have to deal that type of questions with this method only, which we have just discussed.
Yeah.
But sir, we don't have any of the data point like p of x equals to 1, because you are having this data point here. So you are choosing the box and then the coin with x equals to 1, the probability with x equals to 1. So in that case, we just have the probabilities of the two, and you want me to put these p and q values, but what will be the alpha then?
Alpha will give you, right? We will give you.
So sir, alpha, 2 coins in the previous question are. So sir, these 2 coin setup, so is this alpha is 1 by 2?
Yeah, here it's 1 by 2, right?
So in that question number 8 of activity.
Yeah, in that question it is 1 by 2, because they are chosen uniformly at random.
Okay.
Yeah, so yeah, unfortunately I have to move on. We shouldn't spend so much time on that question, because
it's okay,
we have already done these things in stats. So
okay.
So why do we work with log likelihoods rather than likelihoods?
Because it's monotonically increasing.
And easy to differentiate.
Also, the product is there in the.
Yeah, product would be
The
sum of.
product is converted into summation.
Okay, right. So all these three are correct.
Actually, can I tell some?
Yeah.
Yeah, actually, what's happening? We are concerned here to find the what is the at which value it is the maximum, not the finding the maximum value. Suppose we want to find the maximum value, we can't use the log. Since we want to concern with the at which variable it is maximum, then we are able to use the log. And since log doesn't change the maximum minima at certain point, because the log is that making log behind any function, it doesn't change the orientation. That's why it's changed the value but doesn't change orientation. That's why it is good to use the log to find the just value of the maximum.
Okay, so that is one reason which professor mentioned, which is that log is monotonically increasing, so it doesn't disturb the
orientation, yes,
position of the maximum.
right.
But that is only one reason. We should also look at two other reasons, which is from the computational point of view.
Yes.
We are taking the product of many quantities, which are all fractions, and it will essentially cause what is called an underflow, right? So overflow happens when you multiply large numbers. Underflow happens when you multiply very small numbers, a lot of small numbers, right? So that is one reason we convert log product to sum using logs. And the other one is, of course, the monotonically increasing part. Okay, again.
But
yeah.
No, here we are trying to estimate P, and using the product, you are trying to estimate P, R max of P. The same thing can be obtained, the R max of P, using log also, because it is monotonically increasing. And finding P using log will be the same like finding P using product, but the computation will become very easy.
Exactly, yeah. Okay, so I think you are all good with that, so I'll move on. So the MLE for Gaussian is like this. We have seen Bernoulli, now it's Gaussian. So the likelihood is just product of n Gaussians. Again, this is because of the IID, we can say this, right? So yeah, one.
Excuse me, sir. Sir, are we going to discuss all the topics in this lecture, in this session?
Yeah, all the, at least till the end of this week.
So the estimating parameters part also?
Yeah.
Okay, sir. And sir, next session would be the programming assignment one?
Yes.
Okay, sir.
Yeah, so here it's again the independence makes it a product. And okay, so the reason we are able to use the same f for all the endpoints is because they are all identically distributed, right? You're able to use the same Gaussian with mu and sigma square only because all the data points are identically distributed, which means what? They all come from the same distribution, which is Gaussian with mu sigma square, right? So this is what we were doing earlier. Everything is coming from this Bernoulli with alpha p plus 1 minus alpha q. That is why they are identically distributed, right? So same thing for Gaussian. You take log likelihood and then you will differentiate with respect to mu, set it to 0, and you will get the required expression. I hope you are all capable of deriving this log likelihood. Okay, so I'm not going into that part. So if you differentiate it and set it to 0, you'll end up with this. The maximum likelihood estimate for the mean is once again very similar to what you had for Bernoulli, which is the sample mean, right? Yeah, so that is so far what we have done. Okay, so now we go to the Bayesian modeling, right? And when it comes to Yeah, just give me a second. So we saw MLE, right? So MLE is one thing. Next concept is Bayesian modeling. Again, you have done this in stats too. So this is how we go about it. We assume that the parameters are governed by some prior distribution, right? Before even looking at the data, we kind of, based on our own understanding of this domain that we are working in, which is often called domain knowledge, what we say is that maybe the parameter P looks like this, or maybe the mu looks like this. Okay, so I have some intuition as to what my parameters could be even before I look at the observations, right? So this is what is called a prior, right? So the reason it's called prior is prior to observing the data, you have some intuition about the parameters. So this is why it's called prior. Next, what you do is you look at the data, right? You look at the observations. And now what happens is, because you have looked at the observations, that may change your belief about the parameters. And this is again something you will see in textbooks. We use the term belief quite often in Bayesian modeling. So prior encodes your belief about the parameters before looking at the data. Then you look at the data, right? And what that does is that has the potential to modify your belief about the parameters. And how does it modify the belief? Using what is called the likelihood, right? Along the way, something called the evidence gets thrown in. Evidence is nothing but some normalizing thing. And all these things combine to give you the posterior, which is the updated belief about your parameters. Okay, so this equation here will kind of convince you the base rule. You have some prior, you observe some evidence or data. That data modifies your prior by means of a likelihood, which results in a posterior.
So is prior same as a hunch?
The prior is the same as the hunch. So prior, hunch, guess, intuition, all these things are kind
Like,
of
yeah, some little information about the data.
yeah, right. So that is what we call P of theta: prior, hunch, guess, and then you observe the data. So likelihood is what? Given the parameters theta, how likely is it that I observe this capital D? Okay, so given theta, how likely is it that this distribution with this parameter would have given rise to this data? That is likelihood, P of D given theta. In maximum likelihood estimate, what were we doing? We were only maximizing this part, P of D given theta. There was no prior, or you are not concerned with P of theta posterior, all of you are only concerned with P of D given theta. But now that you have introduced something called the prior, you are also interested in seeing how that affects your understanding about the whole problem, and that is why you start working with what is called this posterior. So did you all understand this part? What the prior is, posterior is, likelihood is?
So posterior is updated hunch, right?
It is your updated hunch, yeah, your updated belief. So I believe something about my parameters to be true before looking at the data, which is the prior. I then look at the data which kind of modifies or strengthens, or it could either strengthen my belief about the parameters, or it could move it away from my current belief. But whatever happens, it changes my belief in some sense, and that changed belief or modified hunch is what is called the posterior.
Okay, got it.
Okay, so that is Bayesian modeling essentially, which is what we are doing. One key difference between Bayesian modeling and simple MLE is that here we get an entire distribution over theta, right? In MLE, if you noticed, we got a single estimate called a point estimate, right? Sigma xi by n. Whereas here you are not getting just a single estimate. You can get a single estimate also, But rather than that, what you're getting is something more powerful, which is you are getting an entire probability distribution which you can then play around. Okay, so in our course,
Yes, sir.
yeah.
Yes, sir. In that probability distribution, of course, we will choose the highest probability one.
Not necessarily. You could. That is one way of doing. That is called MAP, maximum age posterior estimate. So that is one way of doing it, but not necessary, right? So there are different ways of getting a point estimate.
Oh, okay, sir.
Okay, so in our course, we are mainly focusing on the expected value of the posterior. Okay, so please remember this. We are focusing on what is the expected value of the posterior. That will be our point estimate. So did everyone understand what point estimate is? Does anyone have a question regarding what a point estimate is? Okay, I hope all of you got it. So now we move on to the only problem which we will look at in the case of Bayesian modeling, which is having a Bernoulli distribution and modeling the prior for it using a beta distribution. Okay, and this is how a beta distribution looks like. As far as formula is concerned, you need to know this formula for the assignments as well as exam. The z is not very important. It's just a normalizing constant. But the coefficient, the powers, the exponents are very important. So please make a note that it is p power alpha minus 1 and 1 minus p power beta minus 1. So, and alpha beta should always be positive. Okay, so now that I've shown you what these two beta distributions are, can you tell me which will be beta of 5 comma 2, which will be beta of 2 comma 5? The blue one or the green one?
Blue one is beta 5,2.
Okay, why do you say so? Any reasons for saying that?
Because alpha is greater than alpha is greater than beta, so it will be left skewed. That's what Sir said in the lecture.
The value
Okay.
for the power is large for small value.
The power is large for small value. Okay.
Means in green, yeah, for blue, this green, as it goes to 1, the value is in point and its power becomes large, so it goes
Okay.
like
Right.
touching.
Okay, that is correct. So the blue one is correct. Whatever both of you said is correct. The blue one is beta of 5 comma 2.
Sir, but I didn't get his explanation. Can you explain it again?
Yeah. Right. So what is happening is P is between 0 and 1. That is the first thing we have to remember. P is the parameter of a Bernoulli, right? And P can be only between 0 and 1. So the support of this distribution is between 0 and 1. Okay, so when P is small, let's take the blue case. When P is small, the value of the density is also small. When P is near 1, right? When P is close to 1, the value of the density is high. So when P is high, alpha should be high for the blue curve, right? If that is why alpha should be greater than beta here. Okay, so whereas for the green one, if you notice, when P is small, what is happening? The density is high. For the green curve, when P is small, density is high. So 1 minus P will be close to 1, right? When P is close to 0. So beta should be high in this case for the green one. Okay, so you can work it out. You'll better understand it when you actually sit down and work it out. It may not be very convincing now.
But sir, if it is so like if P's value is 0.5 and if we take its density as 2, then it turns out to be 0.25. But when we increase it, then it will decrease 0.125, like if we take it as 3.
Good point. Yeah, that's a good point. So what I said is only true if alpha and beta are greater than, right? So this if alpha and beta are 0.5, then the exponent becomes negative. As you said, exponent becomes negative, so it's kind of tricky to understand that. So see, the beta distribution, at the end of the day, is like a very rich distribution, right, with various possibilities depending on what alpha and beta values are. So from the context of lectures, it is enough if you know how it behaves for high alpha, low beta, low alpha, high beta. Okay, what happens when alpha and beta are equal, and say 1 or 2 cases, what happens when alpha is below 0.5, beta is below 0.5. These 4 cases, if you kind of understand, it's enough. Okay, so did you get the 4 cases? What happens when alpha is like really high and beta is low? Then the swapped case, which is beta of 2, 5 like kind of case. The third case is what happens when alpha is equal to beta. Fourth case is what happens when they are below 0.5, or rather below 1, right? Because when they go below 1, then this alpha minus 1 will be negative and things will get kind of tricky. Any questions regarding this? Okay.
So there are 4 cases: high, low, low, high, equals, and what is the fourth one?
Fourth one is when they are like, in fractional values, when alpha and beta are fractions.
Okay.
Also, for this, another way of we can think, since it is a beta distribution, so mean of the beta is alpha by alpha plus beta. Just put the value and check where you are lying.
Very good. Okay, I didn't know this. I didn't know this way of looking at it. Yeah, that is very useful, I think. You can look at it that way also. As Amit mentioned, the expected value or mean is that, and yeah, that's a good way of looking at it. So 5 by 7 is going to be close to 1, whereas 2 by 7 is going to be close to 0. Closer to 0, right? Yeah, I think that's a good way of, a very useful way of looking at it. Thanks. Did everyone get that point?
Yes.
Okay.
Yes. But if we go through that way, like we can identify the peak, but the data is not like 5 divided by 7, that is something 0.71. But the peak is somewhere like around 0.8.
Yeah, so yeah, that is another point. Yeah, that's a valid point. So the peak is actually the mode of the data, right? So the mean will be not the peak. So it is also that. So the peak and the mean are not the same, right? So 5 by 7 is what?
0.7.
0.7. Huh?
Yeah.
Okay, it is kind of expected, right? Because there is a lot of density here, but the mean cannot be the exact peak. Yeah, that's a good point. So yeah, it's a good heuristic, but you have to be careful.
So you saying peak is a mode, right?
Peak is the mode, right? That is the maximum value.
Okay.
Okay, so yeah, thanks for the correction. That is also important. Okay, so how do you describe these two priors in English? That's more important from our ML context. So the blue prior, which is beta of 5, 2, if you want to describe it in English, what will you say? So what is the hunch that this is encoding?
It's the green curve is like it's highly likely to be around 0, highly likely to be less, like
small values.
Small value.
Okay.
Blue curve would be high value, like close to 1.
Okay, right. So that is the hunch that we are saying. The hunch for blue is that we feel that the parameter of the Bernoulli is going to be close to 1, or even more English way of saying it would be, the common man way of saying it would be, I have a strong hunch that this coin is heavily biased to, give me hits all the time or most of the time. Whereas the green curve, the hunch that I'm encoding is, I have a feeling that this coin is going to give me tails most of the time, right? So that is what we are saying. So okay, so I hope you understand that part. And now this is again from the activity question. So you have this hunch about P, and you see this data. So what will be the posterior? Okay, that is correct. Others?
Beta 7, right?
Okay, right.
Beta 11.
Okay, so how will you proceed in general? So there is a formula which I think you all know, but what is the first thing that you will do here?
Count number of
Count
heads,
how many-
like number of one.
Right, count number of ones, number of zeros, then
Number of
posterior is beta alpha plus number of ones and beta plus number of zeros.
okay, that is correct. I don't disagree. That is the formula, but
Okay.
how did we get there? Right, so I want us all to understand Bayesian modeling. So
posterior is directly proportional to likelihood into prior.
okay, right, yeah, that is where I want to start with. So what is the prior for this data set?
Prior is beta.
Okay, can you tell me?
Yeah, P 3 minus 1 into 1 minus P 2 minus 1.
Okay, so P 3 minus 1 into 1 minus P 2 minus 1, which is correct.
Yeah.
Okay, now what is the likelihood?
Likelihood is
P power 8.
yeah. Yes, sir.
P power
Probability of getting
P power
given the data is 1, 2, 3, 4, 5, 8.
Okay, P power 8 into 1 minus P power what?
P power
5.
Okay,
Yeah,
right. So
yes,
that
sir.
is likelihood, and as the someone who pointed out at the beginning, the prior into likelihood, the posterior is proportional to this, right? It is not equal to this. It
Yes,
is
sir.
proportional to this, and moment you normalize this, this will be equal to beta of 11,7, which is the same as saying that beta of 3 plus number of ones plus 2 plus number of zeros, which is correct. But please don't forget that you got this formula after doing all this. Okay, so even if you forget the formula, that's fine. Now, of course, in the exam you need to remember it, but for life, even if you forget the formula, it's fine. But you need to remember the sequence of steps that you took to arrive at this. Okay, so that's all we do in the course regarding Bayesian modeling. So how do we get the final point estimate? You could either use the expected value of the beta, which is alpha by alpha plus beta. So if someone asks you what is the point estimate for this particular case using expected value, you should return that, right? Someone asks you what is the MAP, then you have to, that we haven't taught you, so we won't ask that, but that corresponds to this point, right? Here, let's say it's 0.8. Let's say this is the posterior, then 0.8 will be the MAP for this problem.
MAP is what, sir?
It's the maximum a posteriori as opposed to maximum likelihood. So in maximum likelihood, what you do, you maximize P of D given theta. In maximum a posteriori, what you do is you maximize P of theta given D. Right. So what you will do, for example, here is you will maximize beta of 11,7. Okay, so beta of 11,7, remember, is a distribution. So beta of 11,7 is this 1 by z p power 10 1 minus p power whatever, right? And you will maximize this with respect to p, and whatever maximum argmax you get, that is the map estimate.
The point at which we are getting the maximum.
Yeah, the point at which the distribution reaches its maximum is the
MAP
estimate for
yeah.
So that is all.
Sir,
Yeah.
sir, can you please explain the fourth step in the last slide? Yeah, this one. Yeah.
Posterior is equal to, is proportional to the product of these two, right? So posterior formula is likelihood into prior by evidence, right?
Okay.
So
Okay.
evidence is a constant. I mean, it's a normalizing constant. So you don't need to worry about that.
Okay.
So just to see if you all know this part, if you take the beta distribution, how will you get this z value? What you say that it's normalizing constant, all that is fine, but what is the value? If I want to compute the value, what should I do? Idea what needs to be done to compute the value of z?
Hypothesis.
Okay. So I want to know what z is. Of course, this is not something from the exam point of view. We won't ask all these things, but we use this 1 by z, right? Have you wondered what this z is actually? What property should z have for a probability distribution? No, it is not p into 1 minus p. So if beta, if I say this, beta of alpha comma beta is a probability distribution which supports 0 comma 1. If I say the statement, then how will you estimate z? Come on, I think you have all done stats too, right? You will certainly know this. What is the property of a probability distribution? Most important property for a density function, PDF?
It must
That
be
is
integrated to 1.
integration must be.
Right. So it should the area under that should be 1, right? So how will I estimate z now?
You will integrate.
Correct. You will integrate what from what to what?
From 0 to 1.
Okay, from 0 to 1, you will integrate what?
Beta alpha comma beta.
Okay, right. That is correct, right? So you integrate this quantity here between the limit 0 to 1, and that is what z is, right?
Yes.
Okay, so please remember all these things. Of course, not too very important. I'm not saying that they are. You don't know this, you don't know ML, but still good to know. Okay, so finally we come to DMMs and VMs. It's like the real focus of this week. Right, so why go for GMMs? Okay, so simplest reason is that most of the situations that we'll be looking at are going to be much more complex than coin tosses and heights of people, right? So simple Gaussians or simple Bernoullis won't help us. We need something more powerful, right? Usually in machine learning and related fields, powerful means complex. Complex means powerful. Okay, so we need more powerful models to model these situations. What you see on the right is a classic example of a multimodal data set. Okay, there are multiple modes. If you see, there are 3 modes here. In a typical Gaussian, you have only one mode. It's unimodal. But when you have multimodal data sets like this, a good choice is a Gaussian mixture model. And another term for these mixture models is they're also called latent variable models because they use the concept of latent variables, okay, which you might have seen in the lecture, but we'll also discuss that. So what's the generative story for a GMM? So I've seen the lectures. What's the story?
Generative mixture component.
Okay, you choose a what? Sorry, what is the first step?
Deciding from which cluster data point is drawing.
Okay, that is step 1. Then
Computing the probability of.
We will generate data point from that mixture.
Gaussian mixture. Now it becomes
okay,
a Gaussian distribution. because now we have selected a cluster and the cluster is a Gaussian distribution.
Okay, great. Okay, so sample a point from the mixture, right? In our case, it's okay to call the mixture Gaussian because we are only discussing Gaussian mixture models. But in general, the theory holds good for any sort of mixtures, right? So that's the story. So setup, there are two steps, right? You have K mixtures, capital K, pi 1 to pi K, and we'll always use small k to denote some random mixture, okay? There are K mixtures, so there are K means, okay? This is the different K means. So each mixture has a mean mu1, mu2, so on till mu K, and also a Gaussian, also a variance because it's Gaussian. So how many parameters are there totally for a Gaussian mixture model?
There
K
are
mixtures.
K means,
3K
K variances, K means, K variances, and K mixture.
Okay, so 3Ks, is that right?
Yes, sir. We can eliminate one from these pies because all pies would add to one.
Okay, right, that is right. Okay, so in general we have 3K parameters, but we, in terms of free parameters, if you remember what Professor mentioned, he mentioned the term free parameters. You have only 3K minus 1, right? So the other thing is, are there any other constraints on these parameters? Apart from sigma pi k equal to 1, is there anything else?
So there's lambda.
Right, but lambda comes in the estimation stage, right? As such, for specifying a GMM, I don't need lambdas. So
pi remains between
Pi,
0 and 1.
pi
Yeah,
is between 0 to 1, and summation of pi is equal to 1.
Right, that's true. So both are correct. So pi's are between 0 and 1, and they should all sum 2. Okay, so that is the only constraint on the mixture. Otherwise, your mu sigma can be anything you want, and that is the setup. So yeah, I think this we have all told that this is equal to 1. Yeah, so now we come to the generative process. How do we generate a point? Again, there's two steps, but we'll go into a little more detail. First, sample a mixture index, okay, from these K values using this distribution, okay. One second. Okay, so are you all able to hear some noise from my end?
No, it's
No,
clear.
there's no noise.
No, sir.
Okay, if you do listen to something, please stop me. There's some construction activity going on. So yeah, so call this K. So we have generated K from this. So just so that you all understand, assume that there are 3 mixtures with probabilities, let's say 0.5, 0.4, and 0.1. Okay, so 0.5, 0.4, 0.1, there are 3 mixtures. So if I sample from this, what do I mean by that?
That the chance of coming a data point from the mixture is 0.5, 0.4, or 0.1.
Okay, right. So I hope all of you are getting this, that this whole point of sampling from distribution is something you must know. I think you've already seen this in k-means plus plus, right? In k-means plus plus, this is what we did. We were sampling the means from this distribution of scores, right? The probability distribution generated from the scores. Something similar is what we are doing here. Okay, so once you have k, this zi equal to k, right? So this is the indicator variable, also called the latent variable. Okay, so did you all get why it's called latent variable? Why are we calling this latent variable, and why is this GMM called latent variable model?
I think because it is introduced, you can say after you are getting the data.
Correct, right? So it is introduced by us. We say that this is latent, right? Latent is something that's not explicitly visible on the surface, right? So it is kind of hidden. Okay, so and we are kind of positing that there is some mixture from which this point is coming, and that variable I am calling it Z, right? So this is something we are saying, and it's kind of latent. Okay, so that is Zi equal to K. Now, once you know that, you can start sampling from the kth Gaussian, and this is how you do it. All this should be clear by now. So hope there are no doubts. If there are any, please stop me.
Sir, I have one.
Yeah.
Sir, so all the, you can say, mixtures must have the same distribution. Like in this case, all are having Gaussian, you can say, distribution. So it must be true for all the cases.
They won't all be having the same distribution, right? Okay, so see, when we say same distribution, if two Gaussian distributions are same, only if they have the same mean and variance, right? So they're all Gaussian, so they are same in the type of distribution, but the actual distribution, they are different.
Yeah, I am talking about the type of distribution.
Yeah, you are right. They're all same type of distribution.
They must be same type of distribution.
Yeah,
I'm asking this.
Oh, that's a good point. That is something I don't know, right? So I have limited experience there. So are there mixture models where you use two different distributions? Maybe, perhaps, but I can't say with certainty in this stage.
Okay.
Okay, so please do some research, and that will be better.
Okay.
Okay, so that is the generative process. Now we come to the density of a GMM. So again, if you remember the two coin in a box setup that we did, this is very similar to that, right? So instead of two coins, there are like K coins, and the coin, I mean, you can't call them coins any longer. There are K mixtures, right? And the point X could have come from any of the K mixtures. We don't know. We only know the point X that is observed. We have no idea what mixture it came from. Therefore, we have to do this summation, right? So we have to assume that it came from mixture K, and then it was generated by the corresponding Gaussian. So we have to do this for K equal to 1 till K equal to capital K, and sum all these things. So is this
small
expression?
f is, sorry.
Yeah. So the small f is the Gaussian density of the Gaussian distribution.
Okay. Like PDF?
The PDF, yeah. Probability density function of the Gaussian.
Okay.
Okay, is that clear? So in the lectures, probably you would have seen one semicolon mu k sigma k. I am like not using that, but it's the same thing. Any other questions regarding the density? Because for the next few slides, everything depends on the density. Okay. So what I've done is just replace this with pi k. Okay, that is what it is, right? What is the probability of picking up the kth cluster, or rather the kth mixture? It is pi k. Okay, so that is the density. So what do we do next? Once we have the density, the next step. So what is our goal?
Now parameters are the goal, to find parameters, because now we have modeled our.
That is correct. So parameters are our estimating the parameters. That is our goal. How do we estimate the parameters?
Sir, log likelihood is one method.
Right. So we go back to our maximum likelihood estimate, right? So please remember that there are only two methods that we have discussed in this week. One is MLE, another is Bayesian modeling. So they are generic, right? They are generic methods where you estimate the generic methods to estimate the parameters for any probability distribution and data, right? So here you have data from some distribution you don't know. You assume that it is a GMM, and you also know what the density of a GMM is. Now all that you need to do is compute the likelihood, right? So you're doing MLE for GMM. Okay, so are these two expressions clear? They are likelihood and log likelihood. Hope they are. So this is the next step. I'm just substituting the GMM's density into the log. Okay, now what is the next step?
Differentiate. We'll differentiate.
We have to use Johnson's inequality.
Correct, right? So unfortunately, we have some inside the log, as you would have seen in the lectures. So it's very difficult to work with this. So we have to make use of what is called
Jensen's
the Jensen's inequality. So we introduce to that end some parameters called lambdas, lambda ik, right? So how many lambda ik's are there?
K into n.
K into n, right? You are right. So there are k parameters, capital K parameters for each data point. So there are totally k into n new parameters you are introducing. Okay, we are introducing them, and then what we are doing is, what will be the next step?
So why we are introducing them?
We are introducing them because we find this sum inside the logarithm troubling. Okay, so log of sum of logs is fine. They are easy to differentiate and so on. But log of sums is kind of a tricky thing, right? We have only seen so far how to work with sum of logs. Okay, so we
So
somehow
then
want to.
what this signifies, this lambda parameter, what it signifies?
What it signifies, we'll come to that. It signifies something very special, but what it helps us to do is, it helps us to bring the sum outside the log. This is what it helps us to do. Okay, so I have skipped a lot of steps, but these are all there in the lectures. If you need to understand this essence, that should be enough. So log of a sum of certain numbers, you have written it as sum of logs provided certain conditions are satisfied, which are, this lambda ki should be between 0 and 1, and they should all sum to 1 for each data point. Okay, so is this clear to all of you?
Yes, sir.
Okay, right. So from now on, we'll work with what is called this modified log likelihood, which is what we'll be trying to optimize. Okay, and I think you all remember what Professor mentioned, that this is a bound for the likelihood function. What kind of a bound is it? Is it an upper bound or a lower bound?
Lower bound.
Lower bound, right? So it's a lower bound. Right, you can skip in the so of course you have to go and understand all these things, but you can kind of directly jump to the AM algorithm, which comprises of the following steps. You first initialize your parameter theta using Lloyd's, okay, with k as the number of capital K as the number of means. So you'll get some mu's, you'll get some sigmas. Okay, pi k you can get from. How do you get pi k once you do clustering using Lloyd's?
So the probability of x belonging to a cluster, xi belonging to that cluster K.
Right. So how many points belong to cluster K divided by total number of points, right? That will be your initial value of pi k. Once you do Lloyd's, you will get some clustering. Let's say you have 100 points and 10 belong to cluster 1, 50 belong to cluster 2, and 40 belong to cluster 3. Then 10 by 100 is pi 1, 40 by 100 or whatever is pi 2, rest is pi 3. Okay, so that is how you do Lloyd's and get your initial theta naught. And then until convergence, you do these two steps. One is called the E step, where you fix your theta and get your lambda. The next is the M step, where you fix your lambda, get the theta. Okay, so I hope you are all aware of this, right? So it's enough if you know what these things are, what sequence to do them. So this is the E step, the individual steps. So what is lambda ik? Can someone interpret lambda ik?
Probability of ith element to go in kth cluster.
Right, so that's right. So what is the probability that given the data point xi, it belongs to cluster K? That is what lambda ik means. It means something very clear and precise. So, and you get that using the Bayes rule, right? So between Bayes
Excuse me,
rule,
sir.
yeah.
Sir, I'm unable to derive this formula. Sir said use analytical method using Lagrange multiplier, but I'm unable to solve this.
Right, that is fine. That is not a problem, right? So don't worry if you're not able to solve it. Even I also didn't solve it after watching the lectures. So what you need to know is the following, right? So this is what you need to understand from a conceptual level. You understand the log likelihood, modified log likelihood function, right? So I hope you understand this function. Understand in the sense you are aware of how you obtain this. Once you know that, there is a two-step process you are doing. You are fixing the thetas and then you are optimizing for lambdas. Second step is you are fixing the lambdas, you are optimizing for thetas. Okay, so it is enough if you understand that if you fix your theta and solve for lambda, you will get this. Okay, it is enough if you understand that. You don't need to, I mean, if you are able to optimize, great. Using Lagrange multipliers, if you are able to actually derive that this is what lambda ik is, it is great, but it is not necessary at this stage.
So what is L here?
L is just some index that runs over all the K clusters. Sorry, K mixtures. Right? So you are doing this normalization, right? You are kind of going over all K clusters in the denominator. Denominator is what? F of xi, right? So if you think about the Bayes rule, it is what? P of z given x is P of z into P of x given z by P of x, right?
Yeah.
So the P of x is what? It could have come from cluster 1, mixture 2, or mixture K, right? So that is
all
what
the clusters, the probability for it coming from each of the clusters.
Yeah. So if you go, yeah, exactly. If you go back, this is nothing but the density of the GM. So this is what we are doing. Instead of K, we are using L. Okay, so instead of K, we are using L then. That's all we are doing. Okay, so did all of you get this formula? Because this is what you'll have to use in your assignments. So your assignments, what you'll have to do is, you know the value of theta, basically mu, sigma, and pi, you can compute F and P. If you know mu and sigma, you can compute F. Is that clear to all?
Yes, sir. Yes,
okay.
sir.
Okay. Right, so that is the E step. M step is, again, it looks formidable, but they are quite simple to understand. So mu k is nothing but some kind of a mean of data points. If all lambda ik's were 1, it will be just the mean. But lambda ik's are not 1, so it is what is called a weighted mean. Okay, the weight for each data point is, what is the weight is nothing but the probability that this data point belongs to cluster K. Okay, so I'm trying to compute the mean of cluster K, and I'm looking at all the data points in the data set. That's why I'm summing from 1 to n. But for each data point, I'm asking this question: do you belong to this cluster? So if lambda ik is 0.1, then what can we say? It means that there's a very less chance that this point belongs to cluster K. If lambda ik is like 0.9, that means that there is like a very high chance that this data point came from mixture K. Okay, so this is a weighted mean. In a similar sense, this is a weighted variance. And
sir, here all lambda ik's cannot be 1, because otherwise if we calculate mu for another cluster, then below sum will be 0.
Correct, yeah. So all cannot be 1. So it's a good point. So all cannot be 1.
By all, you mean the sum of lambda ik's is 1?
And he's saying that if all the lambda ik's for a particular cluster, let's say cluster 1 or mixture 1, if all the lambda ik's are 1, which means that if all the points belong to mixture 1, then
I think clustering is not happened in that case.
Yeah, so these are all soft assignments still.
Yeah.
Right? These are not yet hard clusters. So I think that won't happen, but
yes.
Yeah, it won't happen, right? So for that.
Yes, sir, understood.
So mu k and sigma k square, intuitively do you understand? See, you don't need to know how you got mu k. Okay, no one understands unless you are like really hardcore into math and on optimization. You don't need to know all that, right? So what you need to know is just what is lambda ik. Intuitively, what is it? It's a probability, right? Point I going into cluster K, what is the probability? That is lambda ik. Mu k is what? Weighted sum of data points, weighted mean, where the weight is for each data point, how likely it is to go into this cluster. Okay, pi k is what? For cluster K, look at all the data points. How likely is it that they are going to fall into my cluster? Sum all those probabilities, divide by n. Okay, so these are 3 very intuitive formulas, and that is all you need to know for each step and m step.
So can you explain pi k again?
See, pi k, what you're saying is, let's look at pi 1, right? So look at, say there are 10 data points and three mixtures. Pi 1 will be what? You will look at the probability of each of these 10 data points falling into cluster 1 or mixture 1. So you look at lambda 1, 1, you look at lambda 2, 1, all the way up to lambda 10, 1, meaning how likely is it that all these 10 points are going to fall into my mixture. You sum all those probabilities, you divide by 10.
Okay, got it.
Okay, so that is E step, that is M step, and final point you need to know is you can use whatever lambdas you get to do clustering also. Right? So how do you do that? One way to do that is look at all the probabilities for a particular point I, and then you say that the cluster that this point belongs to is that mixture which has the maximum probability. So this is what is called hard clustering. Okay, so that is.
Sir, I don't get the term hard problem and soft problems.
See, yeah. So what we mean by soft is you're not committing to anything. You're saying that see lambda ik's are soft in the sense that I'll just take one example. The slides are kind of done, so I'll share a different tab. Okay, so when I say that lambda, let's take a concrete example of what shall we do? Let's do five points and two mixtures. So you have something like this. This is lambda, 5 points, and mixture 1, mixture 2 on the columns, right? So if I say that for the first point, the points are in the rows, right? For the first point, the probability that it goes to mixture 1 is 0.1. So this should be 0.9. Like for the second data point, I say that the probability that it goes to mixture 1 is 0.3. Then other probability is 0.7. Let's say for this it's equal. For this it's like this, and right. So what we have here is rows are data points, columns are mixtures. So the formula that I am saying is ZI. Right. ZI is what I'm saying. This is argmax. We have an argmax. Yeah. So we are doing an argmax of lambda k I over k, right? So I look at 0.1 and I look at these two lambda values. So since the second mixture has a higher probability than the first mixture, I'm going to say that my first data point belongs to cluster 2. I make a hard decision, right? I'm not trying to be ambiguous and say that okay, 10% of the times it belongs to mixture 1 and 90% of the time it belongs to mixture 2. Instead, I'm saying it is belonging to mixture 2. So I'm making a hard decision there, and that's why it's called hard cluster.
Okay.
Okay, so how do we get these clusters? This is one of the ways. You do this argmax. That is one of the ways to get the. So for example, if you do a hard clustering for this set of lambda values, these are the cluster indices that you will end up with, right? So I need 5 rows and 1 column. So what mixture will 0.1 belong to?
Z2.
2. What about second point?
Same.
Okay, for this I am like unsure. So let's say I go randomly with 0.1, mixture 1. For this
1,
1, right? So you notice that I call this a soft clustering and I call this a hard clustering. Why am I doing that? Because I am harder on my data points here, because I say that first 2 should belong to cluster 2. Whereas here I am not so hard on them. I am a bit soft. And I say that, okay, I still give 10% chance that it may belong to cluster 1. Okay, so that's the difference between hard and soft clustering.
Got it. Thank you, sir.
Yeah. So does anyone have any other questions? How we can, get specific questions? If you have any? Any questions? Anyone?
Yeah, it's related to the EM converges to a local maximum.
Okay.
That was derived. If we do iterative steps, it still does not guarantee any convergence to global maximum.
So we are doing it iteratively, right? EM is iterative, right?
Yeah, I mean, the iteration we take from Lloyd's, and then we start off with like how Sir explained the graph, and we started off with one point, and by theta t plus one or t plus two, we might reach a local maxima. Um, I mean, of course, seeing it on the graph, it's easy to see where the global maxima is. Is it not? I mean, in real life, do we not reach global maxima ever with this step, even after many iterations, or do we accept local maxima as a best effort?
Yeah, so we may not reach, right, because the function that we are trying to optimize is the modified log likelihood, right? So we have kind of moved away from even the function we are supposed to maximize, which is the log likelihood. So we are kind of stuck. We are trying to push the lower bound of the log likelihood upper and upper, but we are not really trying to directly address the log likelihood, right?
Okay.
Right. Any other questions? So, does anyone have this activity practice questions? Specific doubts? Are there any? I don't know if we have covered all of them, but
So there won't be any practice questions from your side, like in MLF we had that solve with instructor sessions where we get different questions for practice.
no, it will be a bit tough because we are also kind of running out of questions. So you would like to do that, but not sure if we'll be getting questions that have enough variety in them.
Okay.
Right. So that is the problem.
So actually, we have very few questions in practice assignments and graded assignments. So and these are very complex topics. So we feel that we need more practice on these topics. That's why
Well,
we are asking.
yeah, I agree, but we also don't know how in what way we can help there. But we'll see.
So you can share some resources where we can study, like we can get similar questions and we can study from that. Our concepts will get more clearer from those resources.
Any textbook will work, right? So see, we are not sourcing our questions from textbooks. So any textbook will work. Only problem is textbooks will all have highly mathematical questions, right? So if you take a Bishop's PRML, that will have from question number 1, it will be completely symbols all through the way, right? So I am not sure how it will help you become stronger in the concepts, but the kind of questions that you want, right, which have like proper numbers in them, that I am also not very sure if we will get it, right? So yeah, so I just want to quickly ask you all if there are any questions in the practice assignment. Any questions, anyone? So were you all able to solve this first problem?
Yes.
Yes.
Okay. Right. So three you're able to solve. How to find the ML estimate for T?
Yes, sir.
Yes, sir.
Okay. Anything else? This 4 is kind of be okay. Question 5 is okay, right?
Yes, sir.
Yes, sir.
Okay. So there are, I mean, what do you think should be the answer? Is it 2 or is it 3? I have given it as 2, but you
So
are
because
fine.
second and third clusters are almost similar. Chennai people and Chennai Chase Glassman.
Okay. Right. Okay. That's nice. So this GMM question, what is the mixture of 3 that you would have known how to do that? So this one, did you get what the probability should be for the 3 mixtures?
Yes, it depends on the height of the cluster. Since
Yeah. All right. So that is also correct. What about question 8? How do you find if it came from a particular mixture. How do you compute that probability? So what quantity does it correspond to from what we just saw? Is it mu1, mu2, mu3? Are we asking that, or are we asking something else? Question 8, we saw several concepts today, right? What concept does it correspond to?
Is it lambda?
Yeah, correct. Right. So it's a lambdas that we are asking here. So what is it? Lambda of -3 with respect to 2, right? So we are asking lambda of this point with respect to mixture 2. So I hope you all know this. Anyone having a problem with this question? 8th question.
No, I didn't get the. I mean, I understood the concept. I didn't get the mathematics of it correctly. I think there's some computation error. So I've asked on this course. But I think it's straightforward.
Okay. So anyone else having a problem? This is just base rule, right? So we are asking P of Z equal to 2 given X equal to -3. So we are asking. Are we asking? We are asking. Right. So what is P of Z equal to mixture 2 given the data point X equal to -3? What is this? This is actually P of Z equal to 2 times. I multiply this with what?
P of X equals to -3.
Right. So I multiply this with the density of the Gaussian given the second mixture. Okay, and I divide this by. Okay, I divide this by f of x equal to -3. So how do I now compute? So this is what f of x equal to -3 given z equal to 2 is 1 by what sigma should be here? Sigma 2, right? So this is sigma 2, 1 by root 2 pi sigma 2, and I do exponential of minus x is -3, so x minus mu whole square, right? So whatever mu2 is, I do that, and I divide it by
2 sigma square.
2 sigma 2 square, right? So it's kind of ugly. So let us. Yeah, so that's better. Okay, so this is f of the Gaussian, right? F of x equal to -3. What is the density of this point? Given that the mixture is 2, is 1 by root 2 pi standard deviation of the mixture 2 into e power minus x minus mu whole square by 2 sigma square. Once you compute this value is done. Okay, now P of z equal to 2 is what? Pi 2. Bro. I already know this, right? So I can replace this by pi 2. The only thing I don't know now is f of x equal to -3. So how do I do f of x equal to -3?
It's the summation of all.
Exactly. Right? It's the summation of all these things. So it's the summation of. Just write it down as I1 f of x equal to -3 given z equal to 1. That is, it belongs to mixture 1. Part pi 2 f of x equal to -3 given z equal to 2. Finally, pi 3, right? Pi 3 f of x equal to -3 given z equal to 3. Right? So this is f of x equal to -3. So you have to do these 3 steps. So something similar is what you have to do. This is finally what in our notation, this is lambda 2 power I, right? So let's say this is some ith data point. So this is lambda I2. What is the probability that this point xi, we call it xi. What is the probability that the point xi belongs to mixture 2? Okay, so that is how you do that problem. Question number 9 we'll discuss in the programming session because that's slightly outside the syllabus kind of a question. So, okay, I hope practice assignment there are no other problems. Any other question? Otherwise, we can kind of wind up. Any activity questions? Anyone had a problem with or? Okay then. So I'll stop streaming now.
Thank you, sir.
Sir, after the graded assignment date pass,